So in this video, I'll continue my discussion of scatter plots and the correlation coefficient, and then I'm going to also add the regression line. So here we're going to have some data so we can see this applied in real-world context. So let's look at what we have here. These are percentages who have used, we have marijuana and then other illegal drugs in various countries. So we want to see if there is an association between these two variables. Is there an association between marijuana use and use of other illegal drugs? So to investigate and maybe answer this question, we are going to look at the association in a scatter plot. We're going to calculate the correlation coefficient and also look at the regression line and see what we can learn. So I'm going to put my data in my calculator using the stat menu, and I'm going to edit my list, but first I'm going to clear them. So I'll add my percentages for my X variable. In this case, that's the percentage who have used marijuana. That's 22, 17, 40, 5, 37, 19, 23, 6, 7, 53, 34. And then their partners are 4, 3, 21, 1, 16, 8, 14, 3, 3, 31, and 24. So let's look at the scatter plot. So I'm going to hit zoom and then option 9. Oops, let's see, I think I have something else in here that we're seeing. I'm going to just take that away. I'm going to clear that, go back to zoom. All right, so here's the scatter plot. So what are we seeing here? As I go from left to right, I'm seeing an upward trend. So that indicates that there is a positive association. So as marijuana use increases by country, as the percentage of the population who have tried marijuana increases, so does use the percentage of the population who have used other illegal drugs. Those things rise together. So there's the positive association. Now, what do we think about the pattern here? Well, I think that these points fall on or near a straight line. It's going to be a line with a positive slope. And so let's actually test that. Let's calculate the correlation coefficient. And I'm expecting to get a positive value close to, but not exactly, positive 1. So stat, calculations, option 4. My data is in list 1 and list 2. And I see an R of 0.93. So R equals 0.93. So yes, I would say there is now this is actually pretty close to positive 1. I would say that there is a strong positive linear association. And in this case, I can say between specifically marijuana use and use of other illegal drugs. Okay, now what if I wanted to have the equation for the line that best approximates this association? Notice here I've chosen linear regression and I have something in the form y equals, now the calculator says ax plus b, you may be used to seeing mx plus b. In this case, a represents the slope. So if I round to 2 decimal places, I could say y equals 0.62x minus, because this number is negative, 3.07. So that's the line that would be the best approximation. If you'd like, you can actually add that to your scatter plot. 0.62x, I use this key here to put the variable in, minus 3.07. So let's go back to the scatter plot. I hit zoom again, option 9. So here we see that there's a line added to my scatter plot. So that's the regression line, and it actually fits the data pretty well. When I say fits, I mean that the points in the scatter fall on or near this line. We say that this line has the best fit. It's technically the least squares regression line. So here I said that R of 0.93 indicated a strong positive linear relation. If you want to determine whether R indicates this linear association, I want to use another tool. And so this can be found as a table in many textbooks and online. And I'll show you one from a textbook. This is, it says, these are values for determining correlation in a population. So first column here, it says N, this is a sample size. So this is basically how many ordered pairs you have in your data set. Now in this previous example, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I go down to the row with 11, I see two values here, 0.602 and 0.735. In the column headers, one says this is the Greek letter alpha, and that says alpha equals 0.05, and the other says alpha equals 0.01. This would correspond to 5% and 1%. These are the chances that there is no correlation in the population, even when it looks like there is one from the sample. So this is basically the likelihood that we could be wrong. There's a 5% or a 1% chance when we say that there is a correlation. So let's see. To make the comparison, so I'm going to say alpha equals, I'm going to write down these two values. For 5%, that was 0.602, and for 1%, it was 0.735. So if R, our correlation coefficient, is greater than the value from the table, and so one of these from then I'll say one of the values from the table. This indicates a linear association. So our R value is actually higher than either one of these. So if we choose the lower percentage here, notice our R value is more than 0.735. So in our sample, we say that we found evidence that there is a linear association. So what we can say is, though, we can qualify this by saying there is a 1% chance, that was the risk that we were taking by using alpha equals 1%, and using this to compare our value of R. There's a 1% chance that the variables are not coordinated in the population. That would be even though the sample data, and that's just the data that we have from these 11 countries, even though the sample data indicates a linear association. Or you could say a correlation. Another point I want to make before I go is correlation does not mean causation. So to show causation, we would usually need a designed experiment. These are just some observations. So there could be other reasons that would explain a cause, like a cause and effect. So a classic example that shows the distinction between cause and effect. This is one that you'll see in many textbooks. And there's even one here from the textbook I'm looking at. It says, as air temperature increases, there is an increase in the number of people stung by a jellyfish. So those things are correlated, so there's a strong association between air temperature and the number of jellyfish stings. But increasing the air temperature does not cause more jellyfish stings. There is another variable that is related to both of those things, and that's the number of people who go into the water. When it's hot outside, more people go to the beach and go into the water, and when there are more people in the water, there is a higher chance of jellyfish stings. So it's not that the air temperature causes jellyfish stings, it's that both of those things are related to an increased number of people in the water. So just be careful in how you interpret this. Correlation, where you can say that these things are correlated, we're not saying that there's a causal relationship. All right, I hope that helps, and I'll see you in the next video.